should make a difference.
Okay. Thanks for that, Siddharth. And yeah, so this is a part 2 of the talk that Sam gave last week. And recall, Sam's talk had the same title, but a different subtitle. He focused on geometrical issues in the sense in which Minkowski spacetime or flat spacetime can be said to approximate curved spacetime in general relativity. I'm going to address the same question, but from a somewhat different perspective, looking at a different class of answer that you sometimes find in the literature. And so just to recall, the question we're focused on here is, what does it mean to say that special relativity is locally approximately valid in general relativity? And so here's the kind of answer that I'm going to consider today, is that the sense in which special relativity is locally valid in general relativity is that the dynamics of matter fields in general relativity are locally approximately those of matter fields in special relativity. In other words, that the way that physics happens locally, even in curved spacetime, is somehow similar to what you would expect from a special relativistic context. So this is quite different from the sorts of stuff that we talked about last week. It's not really about relativity theory. We're making a claim here about the dynamics of matter, right? And so by matter, I mean, electromagnetic fields, small bodies, maybe classical limits of quantum fields, like fields that satisfy the Klein-Gordon equation or the Dirac equation or the Yang-Mills equation. In order for something like this to be true, it has to be the case not just that relativity has some structure, in particular the geometry of space-time has some structure, but also that the laws governing how matter behaves are in some sense compatible with this interpretation of the local validity of special relativity just discussed, that somehow general relativistic matter knows to behave approximately specially relativistic. And so there are kind of two things that need to be cleaned up in order for this interpretation of the local validity of special relativity to be, to make sense. The first is very similar to what we did last week, which is to say, can we somehow extract a clear statement of what we're trying to assert about matter dynamics when we say that it's locally approximately special relativistic. And so this means that we want to ask, in what sense matter dynamics in general relativity approximates matter dynamics in special relativity? Like what do we mean by approximation? What kinds of approximation are needed in order for this to be true? And then relatedly, what kinds of conditions might we place on matter dynamics to ensure or imply that they're locally special relativistic? You can certainly write down differential equations that would govern some kind of matter, which even have some of the qualitative features that you would expect fields in general relativity to have, or field equations to have in general relativity, but which certainly don't in any interesting sense approximate special relativistic dynamics. We'll encounter some examples of those later on, or at least ones that don't seem to approximate special relativity in all the salient senses that you might care about. And so somehow we need to both say what we mean by approximation and also say what sorts of properties of matter fields we're interested in here. But then there's a second question. So we're making a claim about the special relativistic character of matter dynamics. And it's not clear where that claim is coming from and what its status is. So is the idea that somehow in the context of modeling matter within general relativity, we happen to find that the field equations that are most effective at modeling realistic situations happen to be such that there's some kind of approximation to a special relativistic setting, right? So in that sense, you might think, well, okay, so it happens to be the case. It's a descriptive claim about the matter dynamics that we find applicable in general relativity, that it has certain qualitative and quantitative similarities to matter dynamics in special relativity. Now, that does seem to be the case, as in ways that I'll substantiate as we go on. But very often, when you see people talk about the idea that somehow special relativity is locally valid, they have in mind something much stronger than that. Something related to, for instance, foundational principles of general relativity, like the equivalence principle. And the idea is that somehow general relativity enforces a locally specially relativistic character on matter dynamics. And here, I think it's much less clear what's going on. It's much less clear why we should expect physically possible, physically reasonable matter dynamics within general relativity to necessarily have a locally specially relativistic character. And I think saying what goes wrong if you try to introduce general relativity, matter dynamics that are not locally specially relativistic, turns out to be quite challenging. Now, once I've sort of said some things about what we might mean by locally specially relativistic, what we mean by approximation, and so on, given some examples, I'll return to this question. In a sense, though, I think a fully satisfactory answer is going to have to wait for 2 more weeks, because this is part of what Eleanor is going to talk about. Okay. So let me just, I already said the words equivalence principle. Let me just, I have a slide on it. So the kinds of questions that I'm highlighting here are wrapped up with the status of the equivalence principle, especially what has become known as the strong equivalence principle in general relativity. I'm not going to do anything here related to the very interesting historical questions of what Einstein meant by the equivalence principle, what various followers of Einstein meant. And I'm also not going to engage with, arguments from people like Singh onwards about whether the equivalence principle really plays any kind of substantive role in general relativity. I'm going to focus on this idea that matter is locally specially relativistic. Often when people in the literature try to articulate what they mean by that, they'll describe that as meaning that the matter satisfies some form of the equivalence principle. And so there's a kind of indirect relationship between what I'm going to say and forms of the equivalence principle. But I'm going to sort of leave it indirect. I think when Eleanor comes in 2 weeks, what she's going to present is going to take some of the key ideas from this talk, use them to formulate something that is recognizably a form of the strong equivalence principle, and then show how it fits into a network of inferences that make a bit clearer what power the requirement that matter be locally specially relativistic or, as she will put it, satisfy the strong equivalence principle, has in sort of supporting the geometric interpretation of general relativity. But that's not what I'm going to do today. I'm just partly because Jacob asked a question about the equivalence principle last week. I thought I would say something about how what I was going to do today connects to the equivalence principle. Okay, so we'll start with some preliminaries. This is a talk about properties of matter theories. I've got to say first what a matter theory is. Then I'll go through 3 criteria that we extract from various discussions in the literature for what it would mean to say that a matter theory is locally especially relativistic. And then I'll return to the 2 questions that I posed at the beginning here. Okay. So what do I mean by a matter theory in general relativity? For present purposes, a matter theory consists of 2 things. You're going to first specify one or more types of field in the sense of sections of some fiber bundle, so maybe vector fields or tensor fields or spinor fields, whatever it might be. But one or more types of fields representing properties of matter, whose configurations are given by sections of a fiber bundle, and some system of partial differential equations on those fields, whose solutions we understand as dynamically possible field configurations. So basically, I'm giving you some fields, I'm giving you some differential equations on them. What I want to emphasize, though, is that it's not enough to do this sort of just once. What you really expect from an adequate matter theory is that it systematically assigns both field bundles and differential equations to any relativistic spacetime. In other words, I know what I mean by Maxwell's theory, right? By electrodynamics in Minkowski spacetime. I know what I mean by it in Kerr spacetime. I know what I mean by it in Gödel spacetime. I know what I mean by it in FLRW spacetime, right? Any spacetime at all, you give me the spacetime, I can say, well, the fields are going to be 2 forms, and the differential equations are going to be that the covariant divergence of the 2 form is equal to some charge current density, and the exterior derivative of the 2 form is 0. Okay, those are my equations on any spacetime. Now, notice that the equations actually depend on the spacetime. They depend on the equation, on the metric, in the sense that that first inhomogeneous equation relates the covariant derivative operator, and in fact, the contraction of the covariant derivative operator using the spacetime metric with my dynamical 2 form. Okay, so you give me a spacetime, I can give you back a system of equations on a field bundle that, in general, will depend on the spacetime. So matter theory has to do that. And one of the things that I'm building in here is the idea that in order to have specified a matter theory, I've told you both its sort of generic general relativistic character, but also, as a special case, its special relativistic character. Because I've told you, since I've told you what the differential equations are on every spacetime, I've told you in particular what they are on Minkowski spacetime. And so recognizing matter theories as having this character is going to allow us to say what the special relativistic features of that matter theory in particular would be, in a way that will then allow me to compare them to the behavior of the matter theory in general. Okay. And so this is just sort of restating that and introducing a little bit more notation, although I'm realizing that when I made this slide, I changed the notation from the paper in a way that I didn't change it later on in the talk. So I'll clarify this. So a matter theory must determine for each pair MG a fiber bundle B over that manifold and a system of equations on sections of B. I used E here to represent the system of equations. Elsewhere, I'm going to use P, which is what we use in the paper. But so when we see P as a function or a functional of the fields and the metric, that's the same as E here. It's just a system of equations, which can always be written of the form, G and some derivatives of G and of phi together form some algebraic expression, which we said equal to 0, and that's what we understand to be the equation whose solution.
I have a question, Jim.
Yeah.
Is this a geometric way of expressing what the general relativistic law of motion is for matter?
So far, it's just a schematic way of writing down a system of partial differential equations. And so, for instance, Maxwell's equations would be an example of something of this form, or the Klein-Gordon equation.
Mm-hmm.
Right, so we don't need to be talking about like geodesic motion or anything like that. We're talking about field equations.
Okay, and I assume in principle, it could be that a matter theory doesn't work on some relativistic spacetime. So Maxwell's equations don't work on Newtonian spacetime. Of course, that's not a relativistic spacetime, but in principle, it's possible that a matter field is not well adapted or something to.
Well, not every manifold emits a spinor structure, for instance, and so you can't write down Dirac's equation globally.
Right. Yeah. Okay, so this doesn't mean that it has to be that theory has to work on every. It just has to have some way of assigning it.
Yeah, and so on any relativistic spacetime is not intended. The scope of the claim is supposed to be sufficiently flexible that if equations can't be defined on, or fields can't be defined on a certain spacetime, then we can just exclude that. The point, though, is that we're not working spacetime by spacetime. We're sort of defining these theories both for special relativity and for whatever general class of curved spacetimes we're going to be interested in.
Yeah.
Okay. Now, there's actually quite a bit more to say here. What Sam and I did in this paper, I think, can now be seen as the first step towards sort of a more systematic approach to closely related ideas that Eleanor and I worked out in a paper that's on the archive called Natural Theories, which I believe she'll say some things about in 2 weeks. But for our purposes, this is all we need. Okay. Good. So let's move on and start talking about criteria for matter theories to be locally specially relativistic. So one kind of claim that you see quite often is that what it means to say that a matter theory in general relativity is locally specially relativistic is that the equations have a certain form, or at least a certain form when expressed in certain ways. And so here's just a characteristic example from Harvey Brown. It's one of the quotes we had in the paper. I didn't go searching for others, but there are hundreds of people who would put the point in just this way. And so I don't mean to beat up on Harvey in particular. But the idea here is that the laws of physics, the non-gravitational interactions, i.e. the matter theory, take their standard special relativistic form at spacetime point P in coordinates in which the spacetime metric, quote, takes the form diagonalized with whatever your signature is going to be, and the first derivatives of its components vanish. In light of what Sam said last week, one way of understanding what's going on here is that the laws of one way of restating this is that if you take your differential equations governing your matter theory, you write them in coordinative form in Lorentz normal coordinates, then the expressions that you write down look like the expressions that you would write down in Minkowski spacetime in standard Minkowski coordinates. Okay, and so this is a claim about what a matter theory's equations look like when expressed relative to certain specified conventions. This way of, I'm calling this the syntactic approach because this way of doing things is syntactic. It concerns how a system of equations appear in a certain language. And so the language is one of coordinates, partial derivatives adapted to those coordinates, and arithmetic functions of those. And so it's highly suggestive when equations have this character that there's something important about that there's something that we're learning about the structure of the equations. Nonetheless, it's hard to see it as more than highly suggestive. And in some sense, everyone everyone in philosophy anyway, who has written on these sorts of criteria in the last few decades have acknowledged this, that there's something ambiguous about syntactic criteria of this sort. Maybe it's maybe that doesn't really diminish the heuristic value, but it's very hard to extract a clear, mathematically precise characterization of just what we're doing here. And the reason is that we just have a lot of freedom in how we express equations, right? There are all sorts of trivial and non-trivial transformations that you can apply to equations. You can add things to both sides. You can redefine variables. You can work with, different derivative operators expressed relative to different coordinate systems. It's not really clear what properties of equations we're trying to make statements about when we use these syntactic criteria, because the form isn't invariant under many additional arbitrary choices that we can make. Sam and I argue that, at least in some cases, syntactic criteria in this neighborhood can be what we call hyperintentional, which is to say that they distinguish between cases that should be viewed as equivalent. So the idea is that you might have two equations that if you're just thinking about some structural properties of the equations, maybe what their space of solutions is like, maybe what their local space of solutions is like, maybe something about what geometrical relationships you understand them to assert. You might want to say, no, these are the same equation expressed in different ways. And yet, it can turn out that when you take these different expressions and then translate them into coordinates, they don't end up being identical to one another or being identical to anything you would recognize as the specially relativistic form of the equation. And so looking at just the syntax seems to suggest that at most one of these can be locally specially relativistic, even though there's a strong sense you'd like to say in which they're actually just the same equation. And this is just another way of making this point that we have a lot of freedom in how we express equations, and what we'd really like is something that's not about our expression, but what is being expressed. So let me try to say that more clearly. A satisfactory characterization of when equations are locally specially relativistic, in our view, would be one that reflects something about the structure of the equations and what they represent, not something about how we choose to express them, even relative to many choices of background convention. And so for this reason, our perspective is that syntactic approaches may be valuable heuristics, but they're not more than that. What you'd really like is a theory of intrinsic properties of a matter theory, and specifically of the equations that enter into a matter theory, such that we can say what must be true of a matter theory for its equations to have a certain form when expressed in certain ways. And right now, or at least when Sam and I wrote these papers, there was nothing like a well worked out theory of equations and their forms that could support the sorts of inferences that you might want to draw from a syntactic criterion of when a theory is locally specially relativistic. And so the sorts of things that you need to settle in order to have such a theory would be to give clear answers to questions like when are two syntactic expressions the same equation in different forms, and when are they different equations? You'd want to be able to say if two equations agree on their solutions, are they the same equation? If they don't agree, for instance, on their order of differentiation, are they the same equation? Can I have a second order equation that's the same as a third or fourth or fifth order equation? Right? In general, if I write down any equation, I can differentiate both sides and get an implied higher order equation. Under what circumstances is the higher order equation the same as the lower order equation?
But Jim, I have a question. So sometimes when you're taught special relativity, you're told that the relativity principle is that the equations, the laws take the same form in any inertial frame. So you're sort of saying that kind of principle in general is unsatisfactory.
Yeah, I mean, yes, and there are a couple of different ways to see that. So one is that we have perfectly good ways of writing down equations in special or general relativity that don't depend on frame at all. And so they take the same form in every inertial frame, in every non-inertial frame. I mean, they just take the same form irrespective of frame because the expression is frame independent. And so what you're really saying is something else. What you're really saying is, once I take an equation which does not depend on a frame, and I introduce some kind of frame dependence, I can then ask, how does the new frame-dependent characterization vary as I change the frame? And we're sort of taught standard conventions for doing this that, as I say, end up having some heuristic value. The problem is that there are many ways in which I can express these things. Yeah, Peter.
So syntactic seems to imply a contrast with semantic in some way. And does semantic include predictions or things you can do in the world to measure things? In other words, are two equations the same if they lead to the same predictions, or is that not, or you want to stay in the realm of the purely formal?
I mean, this is the last question on the slide is supposed to be suggestive of just that, right? And so one further thing you might demand would be that that two equations be the same if in some sense the theories that you associate with those equations would have the same empirical consequences. That's not what we're going to end up doing. We're going to look at two more semantic approaches that are more about the characteristic of solutions of equations as opposed to how you express the equations. But both of them are going to be motivated by these sorts of more experimental considerations, ways in which you expect the world to be the same locally in general relativity as it is in special relativity.
Raise hand.
Oh, thanks. There's another question. Jacob, go ahead.
Hi there, Jim. Can you all hear me okay?
Yeah.
Great. So I'm a little bit confused. So when I think about general relativity, or I teach general relativity, I talk about the equivalence principle. I do mention these kinds of syntactical questions about the form of equations, but I don't present that way of thinking about the equivalence principle as the primary meaning of the equivalence principle. I usually treat it as a downstream consequence of something that I think is a bit more direct. When I think about the equivalence principle, or I teach general relativity and I talk about the equivalence principle, what I have in mind, and maybe you're going to get to this, and I apologize if you do, but I have in mind observers that correspond to a family of world lines that intersect at some point in space-time, or that come very close to intersecting at some point in space-time. And then the question, and this is piggybacking a little bit on what Peter was saying, the question is, what are the kinds of empirical experiences those observers are going to have? And then I, of course, go back to special relativity, right? At that point where their world lines intersect, or in a very small neighborhood of that point, we should have the principle of relativity, that their observations should be compatible with arbitrary changes in frame, which of course I take to be switching between the different world lines that intersect or nearly intersect that point that corresponds to changing your frame of motion, and that there should be no way to communicate signals faster than the speed of light between those observers. And I take those to be primary, right? Because those are the things that we don't want to let go of, because they could lead to all kinds of problems, paradoxes, and so forth. And then ensuring that our field equations, at least in some functional representation, have certain characteristics of form. I view that as a downstream consequence, a heuristic for guessing the kinds of dynamics I want my matter fields to have, so that the upstream implication is that we will not get violations of the principle of relativity, or the ability to send signals between observers that go faster than the speed of light. So I'm just curious. I know the focus here, at least right now, is on the syntactical structure of field equations of matter. I'm just wondering if this is, we're ultimately going to move what I hope would be upstream to questions about whether, for the actual empirical experiences of observers who correspond to world lines, we're going to bring this back to the question of do they have the right connection with what I take to be the basic principles of relativity. That makes sense?
Yeah, but so Jacob, you've asked this question twice now, and the answer in both cases is at the end of the second talk. So let's just pause.
Okay. Sorry about that. Sorry.
Yep. So yeah, no. This, I mean, I'm surveying things that are in the literature already to focus attention on what seems to be the central point, and then also what I think is missing in a picture very similar to the one you just presented. So let's move on to, okay, good. So let me move on now to two different ways of thinking about this that have a more semantic character. Okay, so, you know, Sam and I aren't the first people who to notice that these syntactic type criteria have some issues. In fact, as I said, many of the people who present them also acknowledge that. And so if we're trying to move on to something that's more about the structure of the equations, here's a proposal from Sonego and Baroni. They argue that the physical properties of wave propagation, rather than the form of the equation, should reduce locally to those valid in flat spacetime, i.e. that the physical features of the solutions be locally the same in both cases. So this is from a paper that is not necessarily hugely influential. Brown does talk about it in physical relativity in connection with these issues, and makes some observations about some approving observations about these sorts of ideas, which is one reason why it makes sense for us to talk about it in our paper. But another reason it makes sense is that they give a really concrete interpretation of what this means that looks prima facie plausible, and I think ends up not working. And the reason it doesn't work, or the ways in which it doesn't work, I think are illuminating. Okay, so what do we mean here by the physical properties of wave propagation? They have a particular idea in mind, which is that the fundamental solutions of a matter theory in curved spacetime should have certain qualitative properties in common with those of the same theory in flat spacetime. And so in the limit, as the spacetime points of the arguments of the equation's Green's functions approach one another, the Green's function for general spacetime should be that of Minkowski spacetime under the same limit. And so this is the Green's functions characterize how point-like perturbations to a matter field propagate an initial value problem. And the idea here is that and sometimes you can build any solution out of Green's functions by integrating the source times the Green's functions. And so there's a sense in which what they're proposing is that we look at the fundamental local structure in something almost like a basis for solutions. And if that ends up looking similar to flat spacetime, then you would say that your curved spacetime equations are locally specially relativistic. Okay, and so here's a concrete example of what that might look like in a particular class of equations that they're very interested in. So fix some spacetime, we're going to consider the bundle of real numbers over that spacetime. And we're going to look at a linear differential operator that they're going to claim is, or we're going to be interested in whether a particular linear differential operator is locally specially relativistic. Okay. So a fundamental solution here is just one which yields a delta function at a point when acted on by a given linear differential operator. And so we're going to be interested in this class of differential operators are going to be the ones which have a second derivative with a contraction with the metric, a mass term, and then this additional term that depends on curvature, where C is some number. Now, this should look familiar. If C is equal to 0, this operator is the Klein-Gordon operator. And so if I were to take this, apply it to a scalar field phi with C equals 0 and set that equal to 0, what I would get is the Klein-Gordon equation. For C not equal to 0, you get something that is sometimes called a non-minimally coupled Klein-Gordon equation. Okay. Now, in the case where G is flat, all of these coincide, right? Because then R equals 0. In that case, they're all going to give rise to Klein-Gordon behavior on Minkowski spacetime. And so this class of differential operators is of interest because it, in some sense, gives you a family of generalizations of Klein-Gordon away from Minkowski spacetime. Gives you a family of matter theories, which in general assign different equations to different non-flat spacetimes, but which all coincide in their assignments to flat spacetime. So I'm going to state 3 facts that Sonego and Ferroni emphasize in their paper. The first fact is that in the case where your spacetime is flat and M is 4-dimensional, then for any point Q, the fundamental solutions are supported only on the light cone based at Q. So this is just a fact for all of these equations, which of course in flat spacetime all coincide with the Klein-Gordon equation. A fact about the structure of the Green's functions of the fundamental solutions, which is that they're non-vanishing only on the light cone based at each point. Here's another fact. For an arbitrary curved spacetime, the fundamental solutions may have support anywhere time-like related to my point Q. So in particular, if C equals 0, then in the presence of curvature, at some point Q, there will be fundamental solutions that have support at other time-like related points, not ones that are only null related to Q. And then finally, there's a unique value of C such that for arbitrary spacetimes, fundamental solutions are supported only at points null related to Q. And that value of C you can show is 1/6. And so Sonego and Ferroni conclude from this that the standard Klein-Gordon equation, understood in curved spacetime, is not locally specially relativistic. The reason is that its fundamental solutions have the wrong properties. Once you look at the actual structure of the equation and the structure of its local space of solutions, you only get locally specially relativistic behavior, they claim, in the case where C equals 1/6. Now, this is not the conventional view. I mean, most people think that the regular Klein-Gordon equation is perfectly locally specially relativistic, that it's the right generalization away from flat spacetime. But the point here is that there are quite plausible things that you might say about what it would mean to approximate flat spacetime, which give totally different answers, and that the form of an equation, the structure of the equation, can come apart. And it highlights a sense in which, I think more concretely, a sense in which claiming that some equation is locally specially relativistic is ambiguous, because we haven't really said what kinds of approximations are supposed to matter for this principle. We haven't said in what ways we want our theory to be similar to special relativity. This is one way in which a theory might be similar to special relativity that gives a very different answer from, for instance, naive syntactic approaches or other kinds of approaches that we'll talk about in a moment. Okay, so that's a candidate criterion of the sort that Sam and I argue is better than a syntactic one. But it's just one, and it gives an unexpected answer. So let me give another one, this one following Jürgen Ehlers. So what I'm about to read a very long quote that I think will sound familiar, because I think it's going to sound very similar to what Jacob described from how he presents these things when he teaches general relativity. So this is from Ehlers, 1973, handbook article on general relativity. Suppose a physical process which takes place in a small space-time domain has been analyzed in the framework of special relativity theory, and one wishes to describe an analogous process occurring in a gravitational field without having a complete general relativistic analysis, a common situation indeed. Then one may proceed as follows. One chooses an event P in the general relativistic spacetime model, situated where the process is assumed to happen, and identifies it tentatively with an event P prime of the special relativistic model. One identifies, moreover, the flat spacetime of the latter model with a tangent space MP of the curved spacetime M at P. And one uses the exponential map to transfer all events of interest which form part of the special relativistic model of the process in question from the tangent space at M to M. The chronometric relations between the events thus obtained will then, because of results analogous to the one that Sam presented in his talk last week, differ arbitrarily little from those of the original flat space theory, provided the gravitational tidal field, R, A, B, C, D, evaluated in a suitable orthonormal frame at P, adapted to the process, is sufficiently small, and one can estimate the deviations if one knows the curvature. It is therefore plausible to assume that if a theory is locally specially relativistic, then, except for error of the order of the deviations just referred to, the model of the process obtained by applying the exponential map is a correct one. Okay, there's a lot going on in these passages. So what I want to draw out from this is the following idea. That a locally specially relativistic matter theory in general relativity is one with solutions that locally approximate the solutions of the corresponding equations in flat spacetime. Now, the idea here isn't that the fundamental solutions have some qualitative feature in common with special relativity, but rather that generic solutions, insofar as so generic solutions for a curve metric will approximate flat spacetime solutions insofar as the flat metric relative to which the flat spacetime solutions are determined approximates the curved metric. Right, and this is what we're taking from Ehlers here, is the idea that there's a sense in which your metric at a point can be extended via the exponential map to give you a flat metric near a point, which will in general agree approximately with your curved spacetime metric near that point. And now we're going to compare solutions relative to those two metrics. Okay. And so this is in some sense, a more focused kind of approximation than the very generic kind of approximation by fundamental solutions suggested by Sonego and Ferroni. So let's call this the G approximating version of the Ehlers criterion. You can see immediately why it would have pragmatic value. In fact, this is what Ehlers is presenting. It's saying it's really useful if this is true, because it means that we can sort of solve problems in special relativity and then have a toolbox for thinking about how to apply those solutions to understand how to model matter in curved spacetime. Okay, so can we actually extract a precise condition from this idea? Ehlers doesn't go in any more detail than what I just read. There are two kinds of barriers to doing so. The first one is to identify situations across different spatiotemporal contexts. And the second one is to say exactly what we mean by approximate. Okay, so in order to do this, we're going to make use of the results from Sam's talk last week. So fix some relativistic spacetime. Choose any point in M. Remember that theorem 1 of part 1 that Sam presented last week tells us that there exists, on sufficiently small neighborhoods of our point P, flat metrics which agree with our curved metric at P and whose covariant derivative operator agrees with the flat one at P. So there always exist metrics, flat metrics that approximate our curved metrics in this sense. Now, remember the way that we've defined matter theories. If I have this region U of P, and I have two different metrics on that region, I can think of myself as having two spacetimes. One spacetime is U with the curved metric that I began with. The other spacetime is U with this flat metric. So I have two spacetimes, and I have a precise sense in which the two spacetimes approximate one another. because matter theories assign equations to space-time, I also now can say what that matter theory says the behavior of matter should be like in my local region of curved space-time and in my local region of flat space-time. So what we're going to do is we're going to compare solutions to those two sets of equations on the same region U of our manifold M relative to two different metrics that have a stated relationship to one another. So this leads to the following condition. We'll say that a matter theory is G approximating if, given any spacetime with associated field bundle B and differential operator P, given any point P in our manifold M and flat metric near P that agrees to first order with G, then any solution in flat spacetime, and given any solution in flat spacetime and any epsilon greater than 0, there exists some perhaps smaller region, O hat, and a field phi on that region, which solves the curved spacetime solution, and where the difference between my curved and flat spacetime solutions is within epsilon relative to some norm. And I'll say more about the norm in a moment. So the picture here is basically you give me any flat spacetime solution, I can find a curved spacetime solution that will approximate it. The important thing is that I've come up with a way of saying what I mean by a flat spacetime solution and a curved spacetime solution. And I've at least put in as a placeholder here the idea that by approximation, what I mean is that the differences in field value expressed relative to some norm or calculated relative to some norm is arbitrarily small locally. So this is a almost mathematically precise statement of what it would mean for a matter theory to be locally specially relativistic. For interest of time, I'm not going to go into a lot of detail about this next thought. I'm just going to say you can do the exact same thing with the opposite order of quantification. So rather than say, given any flat spacetime solution, I can find a curved spacetime solution that approximates it. I can also go in the other direction and say, given any curved spacetime solution, there exists a flat spacetime solution that approximates it. And so in that case, you'd be saying, so in the first case, you'd be saying that if I have a model of something in special relativity, that model can generate a kind of approximate curved spacetime description. This other way of doing it would be to say, well, if I have a model of something, or maybe an exact description of something in general relativity, that behavior is going to be suitably similar to some behavior that I can find in special relativity. So all of the possibilities in general relativity correspond in some way to approximate special relativistic situations. Okay, and so I won't read this out. It's just the same condition, but with the order reversed. Okay, so we now have kind of the definitions for when a matter theory is locally specially relativistic. We can now ask, do any physically realistic matter theories satisfy them? And this is the thing that I think is a gap, maybe the biggest gap in sort of standard ways of presenting the equivalence principle. Because without a precise statement of what we mean for a theory to be locally specially relativistic or to satisfy the equivalence principle, it's not clear what it would take to show that such and such theory that you might be interested in truly has this property. Now, let me say these criteria are stated in a sort of schematic way relative to some norm. We don't have a view that there's a particular norm that should be used in all cases. In fact, we think that the norm should be context dependent. It depends on what kinds of phenomena you're interested in, how you think your field theory or your matter theory represents stuff in the world. But we do think that two things should be true. Number one, the norm shouldn't go to 0 simply because the size of the neighborhood is going to 0. It has to actually tell me about differences in field values at a point. And then two, it should measure differences not just in field value, but also in derivatives up to at least the order of the equations, because otherwise you're going to end up with trivial approximation. Just by getting fields to agree with one another at a point in sufficiently small neighborhoods, they'll agree everywhere. Okay, but with those desiderata in mind, you can actually prove now for suitable choices of norm that certain systems of equations are locally specially relativistic in this Euler sense. And so this is a proposition. I won't read it. I'll just say what it says. It says that, in fact, Maxwell's equations on an arbitrary spacetime are G approximating in the Euler sense for the C1 supremum norm. This establishes that free Maxwell theory satisfies the G approximating Euler's criterion. So you can actually prove that as a property of these equations. The arguments that we use to do so immediately generalize to other linear theories with certain characteristic dependencies on the spacetime metric. So we can show that the Klein-Gordon equation is also G approximating. We can show that Maxwell and Klein-Gordon are also both eta approximating. It's important, though, to note that these arguments rely on the theories being linear. And so as far as we can tell, it's an open question whether the Yang-Mills equation is locally specially relativistic in either of these senses. And it's not something we think that you can just read off of the form of the equation or anything like that. It seems like it's a substantive question about whether or not you can always approximate flat spacetime solutions for a nonlinear theory, even if in some sense it depends on the metric. All right.
So we're
at time, I think.
Yeah, but we started a few minutes late, so can have like 10:35 or something.
Okay, I mean, I don't have much left. I just wanted to come back to those ambiguities that we started with. So what does it mean to say that matter dynamics in general relativity are locally approximately those of special relativity? What sense of approximation is at issue, and what conditions on matter dynamics ensure or imply they are LSR? I think that we've given a number of different answers. We can see first that the answers can come apart from one another. Even plausible looking answers can come apart. So there exist matter theories that are LSR on the Sonego-Ferroni criterion, but are not LSR on the Euler's criteria, and vice versa. And so the wave equation with C equals 1/6, the one that satisfies the Sonego-Ferroni criterion, we actually prove that it does not satisfy the Euler-style criteria, that C equals 1/6 does not have solutions that approximate flat spacetime solutions, and vice versa. Conversely, Klein-Gordon is LSR on the Euler's criterion, but not the Sonego-Ferroni one. You can generalize the Sonego-Ferroni ideas to Maxwell's equations. The same thing is true then. And so the upshot here is that there are many ways in which you could try to approximate special relativity and general relativity. But in general, they're going to be incompatible with one another. And so at very least, more needs to be said about the sense of approximation that you're aiming for if you claim that being locally specially relativistic is a foundationally important principle for matter theories to satisfy. Okay, but what about the second ambiguity? Remember, the second ambiguity is whether or not this is supposed to be a descriptive or a normative claim within general relativity. So I think the question is, once we have these criteria on the table, what actually goes wrong if any of them are violated? Now, Jacob in his question gave, I think, one answer that you would often hear, which is that, well, maybe you would end up with a kind of superluminal propagation that would lead to inconsistencies of some sort or paradoxes. But that's not automatic, right? And so you can still have hyperbolic equations that just happen to be non-minimally coupled or have non-flat space-time type behavior, but which don't involve non-causal propagation, don't involve anything that's obviously problematic. And our example here is just the non-minimally coupled wave equations that Sonego and Ferroni discuss. Right? It seems like clearly violating the Sonego-Ferroni criterion can't be a problem because Maxwell's theory violates it, and Maxwell's theory seems to be the paragon of a successful general relativistic field theory. So violating the Sonego-Ferroni criterion is not problematic, but the converse is also true, we would argue. Even though there are no theories that we're aware of that are known not to violate the Euler's criteria, it's really not clear why these non-minimally coupled wave equations, like the ones that Sonego and Ferroni consider, would be incoherent or unphysical, even though they don't have this kind of approximating behavior. Okay. And so one view you might adopt is that the Euler's criteria are pragmatically useful when they do obtain, but they could, in principle, fail without causing any serious problems for general relativity. Okay, so I'm going to stop there. In fact, there's more to be said here. And so Eleanor and I have sort of taken these ideas and developed them further. And I think in 2 weeks, she'll talk about how satisfying Euler-style criteria, or a version of those criteria, turns out to be related to things like the geodesic principle and the dominant energy condition. And that in cases where those conditions fail, like where the Euler's conditions fail, it would break the geometric interpretation of general relativity. And so maybe something does go wrong. But we don't show that the Euler's conditions are necessary for the geometric interpretation to go through, just that it's sufficient to fit into a sort of a network of inferences. Okay, but that's advertising for 2 weeks from now. The main point for this talk is supposed to be that it's not clear that we have a criterion for when matter is locally specially relativistic, whose violation would immediately spell trouble for a candidate matter theory. Leave it at that.
Okay, thank you. So we unfortunately are out of time, so we don't have time for Q&A. So I'm sure Jim will be happy to answer any questions on via email. And so thank you, Jim, for this talk, and thank everyone for coming. And we'll see everyone in 2 weeks. Okay, thanks.
Thank you, Jim.
Bye, everyone.